Talk about projectile motion, and you should already have a pretty good understanding of motion that is one-dimensional, either horizontal or vertical, but let's put them together. That's really the point of projectile motion, is to break it down and put those two things that we already know together to understand something like, say, this baseball. If it follows the path of a projectile, which without air resistance in our perfect physics world, we're talking about a parabola, then really we can say along this path there is some velocity in some direction. In fact, we can represent that velocity in some direction with vectors, which is why we're studying vectors, so that we can understand then the change in motion as the baseball or whatever happens to be in this projectile motion follows its path. So let's do a little bit of reminding. Vector components for us have mathematical quantity. That is, they have a magnitude, some amount, and of course they have a direction, which is why we get to use the vector to show its direction. And that direction can be established along some coordinate plane as having an angle that it is aimed at. So for example, here's a billiard ball being hit, got a force of 5 newtons at an angle from the x. Again, how we establish that is where we put the coordinate frame. So I'm putting my x and y in the classic traditional setup and showing that this angle that we're hitting the ball at is 40 degrees from the x. And the force has an amount of 5 newtons. That is our resultant force, that is acting. So we can break that resultant force, the 5 newtons, down into its component vectors. That is Fx and Fy, which are exactly the length in the x and exactly the length in the y, because they're exactly the value in the x and exactly the value in the y, add up to be F. So just like we do mathematically with a right triangle, we can say our vectors Fx and vector Fy add to be F, or F is the result of the two components Fx and Fy. Now, and then we can just use simple trig to solve for any of the sides that we don't know, or the angle if that's what's unknown. Okay, so let's go back to our projectile. Every single velocity vector, so I'm just picking one of those along the path, can be broken down into its components. So we have Vx, that is the x component of the velocity, or Vy, the y component of the velocity. And again, we can solve for that mathematically. What's important to us is that we're seeing that the velocity at any point in this 2D motion is actually acting in two different directions. One of those might be 0 at any time. Well, Vy could be 0, which we know is going to happen at the, that's right, top of the path. Good. But it is still acted on in those two different directions. Or in other words, let me put this in a different way, and then we'll solve for them, which we can solve separately. If we look back at horizontal motion, something has already started moving to the right, then we know because of inertia it's going to keep moving to the right. So when we talk about a projectile, we can say really it's this horizontal motion plus, all right, I throw a ball straight up and straight back down. There's our vertical motion, which is changing the whole time because it's acted on by gravity. But if I add these two together, so the horizontal motion added to something that's being thrown up and down, then we get a projectile. This is, for us then, the opposite is also true. That if we look at a projectile, we can actually break it down into, oh, what's happening horizontally and what's happening vertically. And we can and actually have to solve for each separately. Okay, here's the full projectile showing not just the velocity vectors as resultants, but also the components. And at any point in this video that you need to take a stronger look or need more time, please pause it. That's the point, so you can take notes or copy it down as you need. But notice, please, that all of the Vx are actually Vx naught, because the velocity in the x initially is the same as the velocity in the x all the way through the motion. Vy, of course, is changing. As it first is heading upward, it's a bigger vector, and then, of course, because gravity is acting down on it, it decreases until the very top where Vy equals 0, good, and then Vy starts heading downwards. But again, this is just our components of the actual velocity of the ball or whatever was moving in a projectile. Okay, let's take some notes. A few things to write down. We've talked about most of this, but when released, only gravity pulls on the object. So just like we saw in the up and down motion, we're only looking at that negative 9.8 meters per second squared. Since gravity is pulling on it downwards, we actually have a vertical acceleration downwards. We also have no acceleration in the horizontal. There's no force that's acting on it until we get to air resistance, which in our perfect physics world doesn't exist, so we have no other forces acting in the horizontal, therefore it keeps going at the speed that it started at. And we would say then the x direction is uniform motion. And we're going to break both of those down next, but that's the basis of it. X is uniform, there's no acceleration, so ax equals 0. And the y direction is free fall, so a sub y equals g. And of course we know that that's negative 9.81 meters per second squared. Okay, let's write both of these down. Again, pause it if you didn't get all of this written down. But I'm moving on. Some details about the rules then in the x direction. So if we just look at the vx's, here's our same picture that I showed you before with the component vectors. Ax, of course, we know is 0 because it's not changing. Mathematically, we can solve for the velocity. If we know v, we can solve for vx naught as v naught equals cosine of theta. That is the theta naught, the angle at the beginning, or if we're solving vx anywhere else, it would be the v at that point times cosine of theta at that point, because cosine equals adjacent over hypotenuse. So the theta is adjacent to our vx. Most important to us, though, of course, that's constant. So if you solve for vx anywhere, you've got vx everywhere. If we know the distance that it travels, so x, here's the total distance that we went from when we hit the baseball until it hit the ground. Now we know that that is going to be equal to vx naught times the time that it was in the air, which time will be determined, as we'll see in the future when we start doing problems. Time is completely determined by how high we hit it, that is the y component. Therefore, how long did it take gravity to slow it down and bring it back down to Earth? Only operative equation in the x direction, since there is uniform velocity in that direction. In other words, you can't use the acceleration equations that we've been using, not in the x direction. We can use this one to solve for v as delta x over t, or for t as delta x over v, but we cannot use any other equations. Okay, in the y direction. Now we're looking at the y. Of course, we do have acceleration. We can still solve for a component if we know velocity. Freeze frame. Right at that point, what's the velocity and what's the angle? Then we can solve with v naught y as v naught sine theta naught, or again, at any point, the vy is equal to the velocity times the sine of theta, because again, sine is opposite over hypotenuse, and the vy would be opposite in our right triangle. Take the positive direction, I'll show that again so you have that in your notes, but take the positive direction as upward. That's classic. Again, if you set it up the other way, just be consistent. But if we make it up as positive, then of course we're looking at a free fall problem, and ay, the acceleration, is negative 9.81 meters per second squared. In this case, we have uniform accelerated motion. Again, no air resistance, perfect physics world, only gravity is affecting it, so it's uniform, it stays the same the whole time, where no wind gusts or anything else is affecting our motion. In this case, we can use really all of the equations, but only consistent in the y. We can't mix and match x and y, but in the y, all of our acceleration equations work. Okay, let's look at just the velocity vector then. Of course, when you break it down into its components, if this helps you graphically draw a box around it like I just did with the dotted lines, but most important is that we're only looking at the component of it that is horizontal. So in the horizontal, we have a vector that is exactly that magnitude. And in the vertical, we have a vector that is exactly that length and magnitude. Okay? To us, of course, the sum of Vx and Vy, those vectors, is V. And if we move the Vy to the other side, then of course it makes a right triangle, and we can solve mathematically with Pythagorean's theorem. And if we know Vx and Vy, then we can solve theta with the tangent. In this case, inverse tangent is Vy over Vx. Okay. Some problems that you'll be solving, and we're not going to solve any today in this. We're not solving problems today in this video, but a couple different options. One is where you have something that is shot perfectly horizontally. If it's shot perfectly horizontally, no matter what it is shot from, in this case, it's a package that gets dropped. So initially, that is right at the instant that it's going the speed of the plane horizontally. Therefore, its initial velocity is only in the x direction. The nice thing about this is that v naught y equals 0. Okay? Obviously, instantaneously after that, Vy starts to increase, and it's falling, so that's increasing at 9.81 meters per second squared. But the initial V naught y, the initial Vy is 0, and Vx then is your initial velocity, which stays the same through the whole problem. So we'll practice solving problems like this, but that's one option. Another is, of course, that something is thrown or shot at an angle, and it could end up landing at the same height that it was at before. That would mean, of course, in this case, that it landed right here. But in this particular scenario, the boy's throwing the ball, or whatever, a rock, something, a water balloon, probably to hit a kid down below, and it's going upward. It has its peak right here, and we can think of this as 3 different motions. Really, mathematically, it will help us if we can break it down. So it's heading upward, and it's got Vx the entire time. Then Vy right here is 0. Now it's starting to head back downward. Vx is still the same. It continues on. Vy is now the negative velocity in the y, that is a component of what our velocity was over here. So whatever Vy was initially is negative Vy at this point. And then in this case, it keeps continuing down. So of course, Vy is getting bigger and bigger and bigger. And it's not beautiful arrows, but you get the idea that this is increasing in size. So of course, at the bottom, we're talking a very large velocity in the y. Okay, we've solved for just that y velocity. We've solved for just the x. The only difference is that we're putting them together. And of course, it takes a little bit of trig. If all we know is the initial velocity is 20 and it's shot at 30 degrees, well, we can say at this initial velocity, there's some component in the x and some component in the y. And because this is 20 and that's 30 degrees, we can actually solve for it. Vy is equal to 20 times the sine of 30 degrees. V naught x is equal to 20 meters per second times the cosine of 30 degrees. And again, we'll be doing more of that solving, but I wanted to show you that there's really 2 different types of problems that we'll be looking at when we solve projectile motion. And we can go over in class, but I want you to give this one a try. So here's the scenario. We've got an Alaskan rescue plane. Oh, I'll read it for you. That sounds like fun. An Alaskan rescue plane drops a package of emergency rations to a stranded party of explorers. The plane is traveling horizontally at 40 meters per second at a height of 100 meters above the ground. Where does the package strike the ground relative to the point at which it was released? So, of course, we're looking for that distance in the x along the ground with the initial point directly below the plane and the final point at where it hits, where it lands. We also are given that it has an initial velocity of 40 meters per second. Of course, that means to us that it has an initial v naught in the x. So v naught x equals 40 meters per second. V naught y equals That's right, 0. Good. Thank you for playing along. I feel like Dora. Most important thing when you solve any problem in projectile motion is that you establish a coordinate system. So we have to put our x and y somewhere. It doesn't technically matter if you put it at the bottom or at the top, but this is, I think, going to be the easiest, is if you start at your point of origin with your x and your y crossing right at that point of the origin of the motion. But we'll talk more about that later. In this case, this is definitely the easiest place. And you already know that your initial velocity is only in the x, and that's 40 meters per second. V naught y is 0. Okay, here's a hint. When you solve, you have to break this down into 2 separate equations. You're always going to have an equation you're solving for in the x and an equation that you're solving for in the y. In this case, we're looking for the distance in the x. That is, we're looking for delta x. You know there's only one equation in the x that you can use. However, in that equation, we don't yet know time. So you'll first have to solve for time. Since we're already using that equation in the x, the time equation has to come from the y. Okay, and what you'll see, please try to solve this, but is time is based almost, well, exclusively on the height. Of course, we're on Earth, so you know gravity. See if you can solve first for time in the y, that's your vertical equation. Find a vertical equation that has time in it and other things that you know, and then solve for the delta x. Good luck. Thanks for being a part of my first video. Can't wait to talk to you about it tomorrow.